So the thing is that when you have to create a process, you have to use the fork system call, right? So this is what we are going to look into today. For example, you were writing a program like this, and you had saved this program on desktop with the name, let's suppose, lab 5 demo.c, and then you would, at some point in time, you will call the fork system call. So fork system call is something which lets you create a new process from another process. And what I mean by that is something which you may not have uh, thought about previously, although you have been, you know, working with processes being created by other processes your whole lives. But this is not how we are really tuned to looking at processes. So let me show you what I'm talking about. So for example, if I go to the terminal window and I type ps3, so the system shows me, this program ps3 shows me the complete list of all the programs, all the processes running in my operating system currently, and they are related to each other using these lines, these connected lines. And you can see that there's a process called systemd, operating system process, which creates so many different things like this thing, this program, this program, this program, this program. So some of the programs I know about, like Firefox is a program which I ran, I installed maybe, or I ran, so it is there. And similarly, this, for example, this, let me show you the terminal program. This is the terminal program that I'm running. This is the terminal icon over here. So I created that inside the operating system. So the operating system process, systemd, has this as a child process. So we call this a child process. Inside this child process, we are running this bash. Bash is the born shell, which is the shell, or just the command line interpreter, this purple screen. And so it is broken down into two parts. One is the outer layer, which is the terminal program, which is the graphical user interface based program, and inside that the command line based program, which is called bash. And why do I see two bash programs? Because if you look closely at this bottom left corner, you see two dots, and that it means that I'm running, if I do this, you can see I'm running two bash windows right now. This is the first bash window, and this is the second bash window, right? So terminal is the same process, but inside terminal there are two processes. Both are child processes of this parent process. And inside one of the bash windows, which is this one, I'm running another program which is called ps3. So as long as this tree was being drawn on the screen, I was running the program which was called ps3, as long as this tree was being printed. But as soon as this tree finished printing, and we were at this cursor line, so ps3 doesn't exist. But there is no way for us to see this tree again without the existence of this process ps3. So it is always going to be there whenever we print this uh, process tree using the command ps3, because the command ps3 is another program. So it is run, it shows you the process tree inside your command window, the bash window, or the terminal window. You can say either of those things. And similarly, the terminal window also has created some other, like maybe 5 instances of genome terminal, some processes to, for some other functionalities. This is again by design. So once you go through what I'm going to tell you today, you will find out that it is possible for you to create as many processes as you want for your program, to support your program, support the functionality of your program. The power you get from this is parallelism. So all of these things are being run in parallel, right? No question about that. I'm going to demonstrate to you why I make such a statement, that these are being run in parallel or maybe concurrently if you have a single processor. But now, because we have multiple CPUs in our systems, these are definitely being run in parallel, right? So yeah, so the other thing I'm going to show you is the thing which is called the PIDs. So PID is something which is a roll number, which is an identification number, which is allocated to every process in the system. 10 is a roll number for this process, 16 is for this process, and so on. So most of the details of these are unknown to a normal user. So if you simply go and read the documentation of the Linux operating system, you will find out what each of these processes are and what they do. But let's go to the bottom of this list, and you find over here that the bash program The previous time I was running the bash program, and I'm still, by the way, running it. It is shown over here. This one, this window, this maximized window, this one. So this is shown over here with the roll number 2659, which is the PID, process identification number, right? So remember that. Very important word for your this course, PID. So the second time, this window that I created and ran, the bash window had the roll number of PID, which was called 4499, right? So, and then inside this bash window, I was running a program which was called PS. So here you can see that I ran this program which was PS, and I gave some instructions like I want to see all the processes. So if you omit this all process, you will only going to see the last two processes. So uh, so this program is also shown here because as long as this list is being drawn on the screen, it is being drawn by the PS program. So PS program is alive and running. So that's why we can see the word PS over here and the PID is also here. Although that once we are here, this PS program is no longer in existence and this PID is totally gone away. It is no longer there. But another fact that we do not use previously used PIDs. So let me run this thing again and let's see what happens. So now let me use this simple PS multiple times. So you can see my PS program PID is changing like from here 4526 to 4527 to 4528 to 4529, and because I did it so suddenly, so quickly, the PIDs are simply incremented values. But if I waited a bit, for example, now I waited a long time, let's see. Now you see the PID value is not just the incremented value, it is like 5 values ahead. So 4529 to 4534. It means that 30, 31, 32, 33. These four PIDs must be belonging to programs which were created during the 30 seconds that I was speaking behind the scenes. Operating system does that. It creates processes and kills them all the time to facilitate its functionality, of course. Let's now come back to this thing that when this fork system call is it is you can say created or it is called, it is run. When this fork system call is executed by your program, it is going to return a value which is the PID value, and you can, by the way, this is just a variable name, and since it is a variable, definitely it needs to be declared somewhere. So you declare this variable over here with this type, and this type is something which is, by the way, included in a library called this. You also need to include some other libraries. The code is given in the book and in the slides. So the other libraries, one of those will be unistd.h, and the other one will be, so another side note that the process tree can also be drawn in this way. This is your parent process. It has 3 child processes, this one, this one, this one, and this one has 2 child processes, this one and this one. This one has only 1 child process, which again has 2 child processes, right? So you can draw a process tree like this, which will be the task of today. So you will be required to do that on your systems. stdio.h is another library we need. And then now we are good to go. It is going to, be, so starting this line up to this line, all of this code, you have only one process. When you started executing this line inside the fork function execution, somewhere in the midpoint or later on, a new process is going to be created. And by a new process means, what I mean is a separate a new program, absolutely independent new separate program, right? So what happens is that I am going to demonstrate to you that I am true or right about this. I'm going to do some printfs. So for example, if I write over here, I am only one, and if I take this and copy this, and in this part, nothing fancy, very simple. I'm just going to, you know, I'm just demonstrating that this line is a magical line. Before this, there is only one program. After this, there are 2 programs, and the second newly created program is the exact copy of this complete program. So it means that if parent process will print this command, child should also print this command, which is very strange to see at first. Let me demonstrate this to you. So now you see, even if I have written two printfs over here, I can see three lines over here, which is, as I said, very strange for a normal programmer who knows C language or any other language, but he doesn't know operating systems. He will be a bit confused. But we know that by design, the fork system call, the objective of this is to create a new process. And it did. One of these lines comes from the parent process, and the other of these lines comes from the child process. So although we are yet to differentiate between the lines, that which one came from the parent, which one came from the child, but at least we have seen the evidence that two processes are now out there. One of those printed this line, and the other one is the exact same copy of this, so it also printed the same line. And because of being the exact same copy, the newly created process doesn't really go back, because the program counter value in both the processes points to this line. The program counter, or the progress of a program, has brought both the programs, because both of them are the exact same copy of each other. Both of the progress for both processes is also the same, which is this point uh, inside, this program. So parent also needs to continue from here after this line, and the child also needs to continue from this line after this line. Let me do this thing, that let me, after this line, let me type over here, if the PID value is equal to 0, then instead of printing this thing, print I am the child process. And after that, write this check, which is else if PID is greater than 0, and I'm going to copy paste the same line over here, and I'm going to say parent process. Yeah, that's about it. So let's run this line and see what happens. And you can see that this line is printed once. And by the way, you can see the reversal in order of both of these lines. Acha, let me ask you something. When you make a set of checks like these, which are mutually exclusive, you know, both of these checks are mutually exclusive. Either this is going to be true or this is going to be true. I hope you guys are at least that well aware that when you have mutually exclusive things, because if it's the same variable we're talking about, PID, so it can either have the value 0 or either a value which is greater than 0. It cannot be both at the same time. But here you see both are being printed. Again, is it a bug? What's going on? So the answer to that is that due to the design and implementation of this method of creating new processes, the designers have built it this way that this variable PID, which is being returned by the fork system call, which creates a process, the designers, they return different values in different contexts. So when you are in the context of the child process, this variable has the value 0, and when you are in the context of the parent process, the same variable, because now these are not the same variables, these are copies of each other. And again, this can only be known by an operating system person, not by a regular programmer, because he's not aware that after this line there are going to be two. So let me actually make it even more appealing by drawing something like, for example, this is your memory, and inside the memory you were running your program. This was my program, which I have written over here. This is the program, right? At least you agree that this is one instance will be there, so this is that instance. And here somewhere you called the fork system call. And what I am telling you is, and I will try to show you proofs for each of those things, and it should make sense. As a result of this line, exact same replica of this program was created in another address space, and it also contained the line fork. But now, since we have already uh, you know ran this program up to this point, we will be going to the next line than this in this process and in this process as well, because both of these are exact copies of each other. So whatever is written in this region of this program is going to be executed, and in this program is going to be executed. But the thing is that the variable PID, which we use to store the return value of the system call, now is also present over here, right? So PID has two copies now. One copy is seen over here, and the other copy is seen over here. So essentially it can have different values. And by design, it is designed in such a way that here the value of PID is kept to be 0, and in this context the value of PID is something greater than 0. And I'm not going to tell you what these values are. And by the way, where the value is 0, this process is the child process. No questions in that, or no doubts in that. And where the PID value is greater than 0, it is the child process. And what is the reason I'm telling you for this is, it is by design. No rocket science. The designers made it this way. This is just one brick in the big wall of doing all of those multitasking things and running so fabulous programs at the tip of your fingers. Just you got it. The logic behind sending different values to PID is that the designers wanted to provide a functionality for the programmer to differentiate between the code of the child process and the parent process in the same code. Because if you see over here, we're writing only one code and we are running two programs. So now let me create a code block. So this is a code block for this if check, and this is the code block for this. So anything I write over here is the part of the child process, and anything that I write over here is part of the parent process. So I can give a heading to this. This is the code of child process, and I can give a heading to this thing as this is the code of parent process. And how do we know? Because we have applied these checks. So where the context where the PID variable is greater than 0 is the context of parent process. The context where the value of PID is 0 is the context of child process. Again, I emphasize this is just by design, and the logic behind doing this thing is that you want to differentiate between the codes inside the same code, the codes of child and parent. You want to differentiate between both of these. This is the logic. There is another very strong logic behind this value and this value, which is I'm going to later shortly inshallah tell you. Of course, someone can argue that why are you so keen on giving these relationship names, even if I have used the start menu as the parent process and the Netflix as a child, and Netflix is being created from the start menu. So Netflix can be seen as a child process of the parent process start menu. Why are we so interested in maintaining this relationship, even if after Netflix is created and starts running, there's no use of start menu, right? So the answer to that is that even if in this example there is no logical relationship need between start menu and Netflix, there are many other examples where there is need to maintain the relationship, and there is a need to communicate, to give communication capabilities to parent and child both to talk to each other. And the most simple logic behind that is that we want to exploit the multiple CPUs inside our systems these days. We want to exploit the power of parallelism. We want to break down our solution to a problem, an application, the working of an application, into different processes, and we want to exploit the power of parallelism for our application. For our single application, we can use 3 or 4 or 8 different CPUs. But if I simply create a child process and leave it to let it be on its own, a stray process, and I don't have a relationship with that, I will not be able to own it as my own and get benefit of computational power of parallelism that process has. I will not be able to get benefit from that. So that is why this relationship of parent child is there. right? Now I'm going to type over here, instead of I'm the only one, I'm going to type my PID is. So I'm going to use the word actual PID now, because there are two different things. PID variable, this is just a variable PID. Let me call it variable PID. VAR PID. Silly to do that, but let's do that. Variable PID. Variable PID. Because it's misleading, it's a bit misleading when you see a variable PID and you talk about an actual PID. Actual PID is, for example, my roll number is 123, and there are 10 people in the academic office who are mentioning my roll number. So when they are mentioning my roll number, they are actually just talking about a variable PID. But my actual PID is 123. This is a hard fact. It cannot be changed, right? So I'm going to say my actual PID is, and I'm going to use this thing, and I'm going to type over here a typecast of integer type, and I'm going to use this system called getPID. So getPID is a system call which gets the PID of the process which is calling this function, and it returns this. So the return value will be substituted at this place, %d, and it will be printed on screen. Which processes PID are we talking about here, by the way? Parent key. Parent is saying that my actual PID is, and let me actually change it to parent. Parent PID is, because we are certain that before this line there was no child or parent. There was only one parent, right? So let me copy this line over here. My understanding is that the child process will be in this part. Okay. So I could be saying that, yeah, so I'm not going to take that chance. I'm going to write the process where variable PID is equal to 0 says that his PID is the same thing in get PID, right? Let me bring it to one line. So I hope you don't get confused with this. Okay. So this is the same code block for where the PID variable is 0, because obviously you will only be inside this block when the variable PID will be what? 0. So I hope that is actually very simple. So uh, the process where variable PID is 0 says that his PID is this one, and whatever the value is returned. So similarly, the process where PID value is greater than 0 says that his PID is this one. And before that, we are absolutely certain that before this line we are talking about the parent process, because the child process doesn't exist before this point. So we know the PID of parent process, right? So let me now run this. The parent process says that the PID of the parent is, which is a reality, is 5000 in this iteration, and it says that I am the, where does it say? Okay. Uh, Actually, let me, yeah. So I think we can go with this. And to make it a bit clear, I'm going to add some of these things. So the parent PID we know in this iteration is 5041. Now you see it is changed, and within 20 seconds it has gone 40 values up. So I am the parent process, it says, and the process where PID value, variable PID value is greater than 0 says that his PID is 5041. So it means that actually this is the parent process, and we have assumed right. We took the advice of the designers, and the designers were right, we were right, that we are actually, when the variable PID is greater than 0, the return value of 4, we are actually inside the code block of the parent process. This is the evidence right here. And then the second code block says that I'm the child process. Our assumption was that where the variable PID was 0, but the actual PID of the child process using get PID function call is 5042, which is just one PID above the previous one, right? So let's run this a couple of times and see whether at any point we see the same value. So we don't see that. The parent is 5051, child is 5052, parent is 5049, child is 5050, parent is 5047, child is 5048. Child will obviously be always one step ahead of parent, because parent will be created before the child process. Parent is the one who is creating the child process, right? So I won't be going into further details. I truly feel like there should be no more confusion, but if there is, I'm going to um, do some other things like yes. So I'm going to type here printf value of variable PID is, and you can type the same thing over here and see what happens. So the value of variable PID in the parent process is this, and in the child process is this. Obviously, we made the same check, so it is going to be 0 in this block. But I will give you 1 minute to read this line, what is going on over here, and tell me yourselves what is going on.
सर यहाँ पे ये चाइल्ड प्रोसेस की बता रहा है, ये वाली डायग्राम है।
Yes. And so parent process is getting the actual PID of the child process inside of its code block in the variable PID, whereas the child process is getting value 0 in the variable PID. And we are able to differentiate between the both of these things, that this is the child process where PID value is variable PID is 0, and where PID value is greater than 0, this must be the parent process. So I'm going to change these statements now. I'm going to write over here parent says, sorry, child says that his PID is this much, and similarly I'm going to erase this part. And now, because I've shown the evidence and I'm certain that this is what it is, that the parent process says that his PID is this much, right? So now things will be slightly more clearer, right? So the parent process says I am the parent, and the parent says that my PID is 5170, just like before fork it was. And it says that the variable PID value, the value of the variable PID, not any actual PID, the value of variable PID is 5171. And the child process repeats the same thing, and it says that I'm the child process, and my variable value is 0, and my the actual PID of child is 5171. Okay, so now you see that the second benefit of having to have a bigger value of variable PID in the parent process is that without any complex system calling, the parent process directly gets the PID of the child process, so that if it wants to send a message to the child process, it becomes very convenient for the parent process. It knows the roll number of the child process now. If it did not receive this value in the variable PID from fork, it will never know what was the roll number or PID of the process which is newly created, right? So this is the only point where it gets the return value of the PID value of the child process. So that's about it. And another thing that you can use this library, which is called wait.h, and you can force this parent process to wait for the child process before doing anything. So I could run wait. So if wait system call is used after the fork system call, then it is taken as that this is called by the parent process, and it forces the parent to wait for the child process to finish execution unconditionally. So this is what happens. Let me show you. So now you see that the parent did we save? We didn't save. Now you see that the child is being printed first and parent later, and in all the previous iterations, parent was being printed first and child was being printed later. So this reversal also shows you that there was parallelism going on, and now we have made it sequential, that we have forced the parent process to wait for child to finish execution. Therefore, child is printing first and then the parent is printing, even though they are absolutely parallel independent processes. Now let's go to do something. I'm going to do something over here. I'm going to get rid of this wait thing, and I'm going to print a for loop, something in the for loop, int I equal to 0 and I less than this. I'm going to print a p from the parent process in loop, a very big loop. So okay, So now you see that you will find out that there is something going on. Like here you can see that let me zoom in. Okay, so here you can see that the parent process was printing, suddenly the child process printing, and suddenly the parent is again printing. Did we code anything that said that now parent should print, now child should print? No, we did not. We simply said for 1 million times child should print C's, for 1 million times parent should print P's. This is the simplest code possible. But here you can see there is context switching going on. The operating system is changing the context from parent process to child process, and then it is changing again the context from child process to parent process. This is what multitasking is all about, right? So you will see these switching so many times because I've done it for such a long printing. So you see P's, C's, P's, C's, all of those things so many times, right? One last thing, and which is that we leave this like this, and there is a possibility that you would, and I'm going to get rid of these for loops.
So
There's another command called execlp. It allows you to run a previously made or compiled program inside the hard drive like this, and there are some parameters we don't really are not going into the details of this. So this line is essentially going to simply run this program called ls, which we have been running before in the command shell. And let's now do this, compile this program and run this program. And you see that after child printed what we asked it to print, it has uh, it has run the ls command from inside the code, not from, like, we could do this ls, but now ls is being run from the child process that we created with the PID value 5345, right? So this is also possible, but execlp command overwrites or erases the address space of the child process and populates it with the code of this new program. So if I were to take this line and bring it over here, essentially what would happen is that as soon as execlp will be executed, all of this thing, all of this thing, all of this thing will be erased from the address space of the child process, even if the child process was the clone, as someone said, clone of the parent process, exact copy of the parent process. Even if that was the case, now because you have run the execlp command, all the uh, address space of child process is now overwritten, and because it is overwritten, it is erased. You will not see the printf values of these things. So let me demonstrate, and if you do this and this, oops, now you see that all the no, I think we did not save it. Now you see that child, no printfs from child are there, only parent printfs are there, but child is simply doing the ls, and because now all the code of child is erased by the ls program, you don't see the child printfs. Got it? So this is the objective and the shortcoming or the side effect of using execlp. But if you bring this line execlp from here to here, then you will be able to do, because whatever you're doing it before exec command runs. So you can still do things in the child process which are other than the the new program you want to run inside. But once you run this inside the child process, you will lose all your code inside the child process. Of course, parent will still have all the code. Any questions? I totally understand that this is an absolutely huge paradigm shift of programming, and it leads to parallel programming, which is even further complex, which will inshallah have a look at in slight details. But you should have this concept very well understood, that how a child, and by the way, it's same in most operating systems. Windows does the same things, Linux, Ubuntu, Android, all of those. So whenever a new process needs to be created, number one, it is created from some existing process, and that existing process becomes the parent of the newly created process, and the newly created process mostly is called the child process. And the reason why PID needs to know the ID of the child process is that probably it may, I'm not saying it must, it may need to communicate with the child process, and if it does, if it wants to do that, it can do that using the id which it of the child process of which it now knows. And similarly, what if the child wants to talk to the parent and not how will that happen? So you will simply write down these. I'm going to copy this line, and child says that my parent is, and you're going to use another system called get ppid, get parent pid. And now let's see what happens. Let's get rid of this execlp and let's run this. You see that we knew that parent is 5461, child is 5462, but from the code of child, now we are saying that child says that my parent is 5461. So it means it is possible for the child to find out its parent's pid, because there is only going to be one parent. A child cannot have two parents, only one parent. So but the parent can have so many children, of course, right? It will be tedious to find out the pids of the children from a parent process. But if you were uh, doing the things rightly, you would simply save the value of the return value of the fork, and that will be the child's pid over here in the parents context. So now everyone has everything. Child knows its own PID and its parents' PID. Parent knows its own PID and its child's PID. And if it creates more children, it will obviously get the PIDs of all of those as well. You can create every time you call fork, you can use a different variable, or if you're doing it in a loop, you can use an array to in every iteration store the new PIDs in different array elements. Any questions?